pre-calc, we get to do two quick little examples. They're basically the same examples we did in class, but just if you need a little refresher. So it says, give a formula for the extended function that is continuous at x equals -3 if f of x is equal to x squared minus 9 all over x plus 3. Now let's think about it. If I plug in -3, I would get -3 squared minus 9 over -3 plus 3. I would get 0 over 0. And I notice that it's actually a whole, right? In my numerator, I have the difference of squares, x plus 3 over x minus 3 all over x plus 3. And I see that shared factor, meaning I have a whole at x equals -3. So of course the question is, how do we extend this function so that we can fill in that hole? Well, I'm going to find the limit as x approaches -3 of this function. So in this case, I'm plugging in -3 into my limit as x approaches -3 into my function. So we had x plus 3 over x minus 3 all over x plus 3. I already know that if I plug it in, I'm going to get 0 over 0. So I will just automatically jump to that step of crossing off these shared factors. And so I'm left with -3 minus 3, or a -6. This is my limit. What does that mean then about the extension of the function? Well, I know that I want to look like the original function everywhere that I can, which is basically everywhere except at x equals -3. So my new function will be, I'm going to name it g of x just to say that it's different. It's going to be a piecewise function where original x squared minus 9 over x plus 3, I want to be that function everywhere except the problem. So that would be as long as x is not equal to -3. And then I am going to fix the problem by plugging in the hole. I'm going to be equal to -6 if x is equal to -3. And that is our answer. We have extended the function to make it continuous. Another example, again, very similar to one we've already done. A function h of x is defined as follows. Find a value of k that makes our function continuous. H of x is equal to e to the kx from 0 to 2 and x plus 2 from 2 to 5. Now for this one, I don't know offhand what e to the kx looks like. Well, we kind of know, right? E to the x we know kind of looks like this. And the line x plus 2 is a line with a slope of 1. But it's not as obvious as the last one. However, we can still do the same thing. If we want these functions to intersect at the same point, we want their x values to be the same and the y values to be the same. In this case, the x value we want is 2. And to say our y values are the same would be to set the functions equal to each other. E to the kx is equal to x plus 2 at x equals 2. And now we solve. We plug in 2, x equals 2 everywhere we can. So I really have e to the 2k is equal to 4. And now we have to solve this. But don't stress out. It's not as hard as it looks. This is an exponential function. Remember, we need to get rid of that exponential. So I'm going to take the natural log of both sides. On the left here, the natural log of e to the 2k, well, we cancel out these pieces and we're just left with, the exponents. 2k is equal to the natural log of 4. Now I can solve for k. Natural log of 4 divided by 2. And while this is a 100% correct answer, we could do a little bit more, and I'm going to just show you because why the heck not? K is equal to, I'm going to make it 1/2 natural log of 4. All I did was change that divided by 2 to be a coefficient. Using our properties of logs, 1/2 becomes an exponent. So I really have natural log of 4 to the 1/2 power. Anything to the 1/2 power is really the square root. Natural log of the square root of 4, and the square root of 4 is 2. So this is another correct solution, although this is totally fine. Those are the two examples. I hope you have a lovely rest of your day. Please let me know if you have any questions.